I make a short introduction?
So we're optimizing. Oops. Okay. Now this B star, this kind of polytope, where we are looking at inequalities xi minus xj at most something, this comes up a lot in the literature. So 3 occurrences of names, how this is called. So in the optimal transport literature, this is called the Lipschitz polytope. So think about this and as a Lipschitz condition mostly in the continuous case. In tropical geometry, in the setting of the min plus or max plus algebra, these things are called polytropes. So this stands for tropical polytope. So these are objects that are both classically convex and tropically convex. And so this is called a polytrope. In algebraic combinatorics, on people who study representation theory, these things are called alcove polytopes. So these are objects that come up in many, many different names. In tropical geometry, there's a new book that I'd like to advertise. Michael Josvik just came out with a new book called Essentials of Tropical Combinatorics that's very much geared towards discrete optimization. And again, these kind of polytropes play a big role. So this is the dual of the unit ball, it's the feasible region of the linear program. Now, the other ingredient in the title was independence model. So independence model refers to a statistical model. So here's a cartoon that illustrates the geometry of maximum likelihood estimation for discrete statistical models. So this cartoon is from an old book I was involved in called Algebraic Statistics for Computational Biology. So here, this triangle is a cartoon for the probability simplex. So there's the space of all distributions. Then the red wiggle is the model. So these are all the distributions that describe some statistical or physical situation. The data gives rise to an empirical distribution. So whatever data we collect gives an empirical distribution at some point in the simplex. And in estimation, we would like to learn the best distribution, or distribution p hat, that best approximates the data. Now, you can see this need not be the Euclidean closest ball in the Euclidean distance. This is a closest ball in something called Kullback-Leibler divergence. And often the way this is given in statistics is by way of a parametric representation. So often there's a parameter space, a low dimensional parameter space, and then the model is actually the image of the parameter space under some map F, and really, rather than finding the optimal distribution p hat, one wants to define the optimal parameter value. So with that in mind, a discrete statistical model is any subset a priori of the simplex, but here in this talk, we assume that M is compact and is the zero set of some polynomials. So then the Wasserstein distance, given the data from the model, is simply the solution to this parametric linear program. So I'm given a distribution, that's my data vector, that's now mu. Then the Wasserstein distance induced by D to the model is the minimum over all distributions mu in the model of the aforementioned quantity. So this is the distance I introduced 10 minutes ago. And to spell it out again, so this is minimizing over all points in this red model of maximizing over the polytrope, the feasible region of our optimization problem. So solving this min-max problem means solving a non-convex optimization problem. So the inner optimization problem is linear programming. It evaluates the Wasserstein metric, but we want to find the closest point. So I've given my distribution mu, I want to find the Wasserstein closest point in some model. Now the model we're going to be interested in here in this talk is the most basic model, the independence model for discrete random variables. So suppose you have 2 binary random variables. Then the joint distribution is given by a 2x2. Joint distributions are given by a 2x2 table. And P and Q are the parameters. So let's say one random variable is whether you are in Austria or not. And the other random variable is whether you wear glasses or not, right? And P is the probability that somebody lives in Austria. Q is the probability that 1 minus P is the probability you're in Germany. And then Q is the probability that you wear glasses. 1 minus Q, you don't wear glasses. Well, then, you know, Radu and I would be at opposite corners of this 2 by 2 table, right? So this probability table, we have these entries, P and Q are non-negative between 0 and 1, and notice that they have to sum to 1, right? So pictorially, the model is this surface, this ruled surface inside the tetrahedron. So I have 4 possible states: Austrians glasses, Austrians no glasses, Germans glasses, Germans no glasses, or ACGT if you like biology, and then independence means being on that surface. Now, typically, of course, in applications, we have more than 2 random variables. We might have many random variables. In that case, matrices become tensors. So in general, by an independence model, I will be meaning a collection of matrices or tensors if I have more random variables of rank 1. It's particularly interesting to think about symmetric tensors. They come up a lot, just like symmetric matrices. So if here P is equal to Q, this would be a symmetric matrix. So here is the picture. This Rubik's Cube is a picture of a 3 by 3 by 3 tensor. So maybe you have 3 ternary random variables. So income, low, medium, high, hair length, low, medium, high, weight, low, medium, high. And of course, in the pandemic, we're all moving towards high. So this is our 3 by 3 table. But if these are identically distributed, then we have a symmetric 3 by 3 by 3 table. And it's always a good exercise. And I'm embarrassed to pose this in front of Christian Kattenthaler. So how many distinct entries does a symmetric 3 by 3 by 3 table have? Well, a general tensor has 27 entries, but if it's symmetric, there are only 10 distinct entries. Right? So color-coded here. And here again is the cartoon. So here's some model. And here we have the unit ball or some ball. This is a polyhedral norm around the data point. You want to find the closest point. So you can see pictorially we are blowing up the unit ball until it hits the green model. Now, I'm a computer algebra person. This means I like to solve small optimization problems exactly. I like the truth, right? Algebra is the study of the truth. So let's find the truth for 2 by 2 matrices. To set this up, I have to fix a metric on the underlying state space. So this is the 4-element set 2 by 2. And the L0 metric on this graph. So this is the given metric space. This is the 4 by 4 matrix I start with. This induces a metric. This turns the tetrahedron into a metric space by the Wasserstein construction. And then here's a little theorem that says the distance function from the data distribution is given by this piecewise algebraic explicit expression. So this is the actual formula in measuring the Wasserstein distance from the surface. Now, the way this works is there's a distinction of 12 cases. So it looks like 8, but they're really 12 because there's an absolute value involved down here. So it's 4 plus 4 plus 4. So then there are some inequalities here, some algebraic inequalities on the entries of the given data distribution. And then if you happen to be in this region of data space, the optimal distance is given by this quantity. Down here, if you're in one of these regions, it's rational, otherwise involves a square root. So this is the solution of this parametric optimization problem for our surface. Here's an even simpler case. This is symmetric 2 by 2 matrices. So in genetics, this is called the Hardy-Weinberg curve. So here, this is the model. This is symmetric 2 by 2 matrices of rank 1. And here the distribution, so the optimal solution is given by 5 cases. So this triangle is cut into 1, 2, 3, 4, 5 regions. And on each region, I'm indicating the optimal value. So this is the optimal value function. And then, of course, there's also the solution function that takes the data distribution mu to the optimal distribution, which is the point on the model. So interestingly, if you're up here in this rhombus region, all of points in the rhombus region get mapped to this top point on the parabola. which is this point down here. Okay? So what do we learn from these solutions? So these are, of course, very, very small. And people in your audience will ask, well, does the scale? That's an epic question, right? Does algebra scale? Does mathematics scale? Well, I'd say in some sense that's your task, right? We're producing ingredients, building blocks, precision medicine for small problems, and then, of course, integrating this into larger systems is a separate task. Let's talk about the complexity of this optimization problem. And I like to make a point that, in my view, applies to many, many, many optimization problems, polynomial optimization problems. The first observation is that the optimal value function, as well as the solution function, is piecewise algebraic. Right? So you can see this. There's a case distinction of inequalities. So they are algebraic inequalities. And on each piece, we have an algebraic function. So this is a piecewise algebraic function. Solving the optimization problem means evaluating a piecewise algebraic function. Well, on these small problems, how do we do this? Well, we divided the problem in two tasks, right? First is to identify all or some of the pieces, to somehow give a description of the pieces. And then we gave a formula on each piece, right? So in blue is identify the pieces, the 5 pieces here, and then, or whatever, 12 pieces over there, and then find the formula on each piece. Now, these two tasks both have a high degree of complexity. And I like to say that the blue task of describing and studying the pieces is a task of combinatorial complexity. Okay, so we have an optimization problem with many, many different, pieces, and the combinatorics offers, a large degree of combinatorial complexity. The second task, if you are inside one of these regions, is a task of algebraic complexity. You need to evaluate an algebraic function. You need to solve a system of algebraic equations. That's an algebraic task. And these are different sources of complexity. So for example, linear programming has a high degree, or fairly high degree, of combinatorial complexity, right? So still outstanding open questions about the complexity of linear programming, but that's an issue of combinatorial complexity because the algebraic complexity is trivial, right? From an algebraic point of view, solving a linear program means solving a linear system of equations. Once you decide what the optimal basis is, you need to solve a linear problem, which has no or very little algebraic complexity. On the other hand, if you have a polynomial optimization problem without any constraints, sometimes you have no combinatorial complexity, but there's still a high degree of algebraic complexity in, say, solving the KKT equations. Okay, so it's very important to separate the two. We see this in semi-definite programming. We see this in game theory. So finding Nash equilibria. Well, again, for 2-player games, there's combinatorial complexity, but no algebraic complexity. But for 3-person games and more, we have universal algebraic complexity because arbitrary real algebraic sets can be encoded as the set of Nash equilibria of a game. So we have sort of ultimate algebraic complexity in those situations. Okay, so I'd like to talk about the blue and the red complexity for our problem a little bit. Which brings me to this picture, right? So the combinatorial complexity raises the question, how many faces does the unit ball have, right? So imagine in this cartoon that the surface of this green sphere is our model. Let's pretend our statistical model is the surface of the sphere. Let's pretend the small green ball is the data point. And let's pretend the cube represents the unit ball in the metric, or represents a ball in the metric. Well, what are we doing is, we're starting with the data point. We're drawing a small unit ball around the data point, and then we're growing the ball. We're growing the ball until it touches the model for the first time. Right? Now you can see, depending where the data point is, it could be here or here or here, we're growing this cube, we're growing the unit ball until it touches for the first time the model. And combinatorially, there is, three possible scenarios that can happen, right? Either it could touch along a facet or along an edge or along a vertex. So it could touch along a face of every dimension. So therefore, the combinatorial complexity question is, how many faces do we think the unit ball has? And how can we sort of deal with this combinatorial complexity of the unit ball? That's the blue question. Now, the second question of algebraic complexity is, what is the degree of the critical variety? Suppose we knew that the data point is here, and we knew that the tangency that certifies the optimal solution is along an edge, is along a particular face or a particular face or a particular dimension. Then there will be an algebraic system of equations, a polynomial system we need to solve. And this is an algebraic geometry problem, right? What is the degree of the critical variety? How many complex critical points do you have? How do you solve these equations? So the blue question is a question of combinatorics or combinatorial geometry. And the red question is a question of algebraic geometry or intersection theory. So for example, on the blue question, polytopes and their F factors, just an illustration of one proposition from the paper. So suppose the finite metric space is actually given by a graph, right? So we start with a graph on n vertices, and the metric we start out with, the metric d, is the graph distance in this graph. This is very typical in the application. In the independence model, we might start with the graph distance on the cube or an appropriate simplex. Then the Lipschitz polytope or polytrope is given by these very simple inequalities. Just xi minus xj is at most 1 for every edge. So only the edges are facet defining. The non-edges, inequalities for the non-edges will not be facet defining. And these are all the facets when G is a bipartite graph. Okay? So the cube, of course, is a bipartite graph. So and here, if G is the K cube, K-dimensional cube, then you can analyze, what the vertices are. So this is our, unit ball, appropriate polytrope, and the vertices have a combinatorial meaning. So they're in bijection with proper 3 colorings of the graph, one vertex of each, with one vertex of a fixed color. Okay, and then crank this out, right? So for cubes of dimension 2, 3, 4, 5, 6, the number of vertices, of course, grows rapidly. So k is equal to 6. So you want to solve this for a binary independence model with 6 variables. Then, you have this quantity, 33 billion roughly vertices. So this would be, the total number of vertices. So enumeration gets already quite difficult, and we have to use different techniques. So in the project, we computed the unit balls for some small independence model, and the combinatorics is an interesting research direction in its own right? So this blue complexity of the unit balls, the Wasserstein unit balls or polytropes arising from these situations, is an interesting topic in its own right. Maybe I'll pause for a question because I'm going to inflict some algebra on you in the next slide. So this is supposed to be the pretty combinatorics, and the scary algebra is coming right up. Okay, then let's move on. So here's a little bit of algebraic geometry. So this is the second problem. So let me be clear again, right? So one topic is how many faces does the unit ball have? And, maybe 33 billion, right? And then we have to ask the question, how do we organize this? How do we design algorithms that address this combinatorial complexity? But suppose we could handle the combinatorial complexity and we're down to solving a particular system of critical equations. We have to address the KKT condition coming from a particular scenario of tangency. What is the complexity of this algebraic problem? Okay. So let's assume that M, our statistical model, is smooth. So it's a manifold. Right? So we have a manifold that lives inside the simplex. Let's give ourselves a linear functional on the ambient space and also an affine space of some dimension R. And let me, for the purpose of this theorem, assume that they're in general position relative to the model. So I have this model M, think about the green surface of the sphere, or think about my independence model, and I have a linear space of some dimension and a linear function. Then let's look at the following red optimization problem. Minimize the linear functional L over the intersection. So M is the model. Then I'm going to cut my model with a bunch of linear constraints, fixed number of general linear constraints, and I get an intersection. And over this intersection, I want to solve, maximize, or minimize a linear function. Now, this theorem says that if M is an algebraic variety, then the rth polar degree is the algebraic degree of this problem. So by algebraic degree, I mean the number of complex critical points. Now, there's a couple of questions. Well, first question is, what's the polar degree? Well, if you know what the polar degree is, that's a concept from intersection theory, then this is a theorem. If you don't know what the polar degree is, then this is a definition. So for most people in the audience, take this as a definition. So there's some quantity delta R that we can compute using intersection theory that gives us this number. Now, why are we interested in complex solutions? So I should maybe digress for a second, because that's the only way we can get an actual notion of degree, right? So we're solving an algebraic system, a system of polynomial equations. Now, of course, we want to find a real solution, or maybe a real positive solution. But the only way I know how to certify that we actually got the optimal real solution in a more general non-convex situation is to find all complex solutions. So state-of-the-art software, numerical homotopy methods, in principle, you have to track the number of paths, which is governed by the number of complex solutions. There's no way around it. I know of no method that would guarantee the solution that I want over the reals that only looks at the real solution. So we need the number of complex solutions. Algebraically speaking, you have your KKT equations, you type them into your favorite computer algebra system, say Mathematica, you eliminate all but one of the unknowns, and you're down to one polynomial in one variable, and that's the degree we're interested in. Now, in our case of independence models, they're known as Segre-Veronese varieties to geometers. These polar degrees are known, and they're combinatorial formulas of the kind that Christian Kattenthaler and his group like. So recent work of Luca Sodomako gives polar degrees of Segre-Veronese varieties. So for example, P1 to the K. So this is the situation of K binary random variables. So the K-dimensional cube. So in the application, we call this the K-bit independence model. Well, the R minus first polar degree is this explicit expression that depends on K and on R, right? So K is the number of random variables, R is the dimension of the linear space, and this is a formula. Now, so this gives a non-negative integer, and as always, of course, it would be better not to have an alternating sum, but this is it, and so you can compute this ahead of time. So here in brown are just a couple of keywords, so Chow rings, Segre glasses are used to derive these kind of formulas. Let's look at some examples. So here's algebraic geometry these days very much meets numerical mathematics. So this is the example just for matrices. So I have two random variables with finitely many states. So I'm talking here about, let's say, 4x4 matrices of rank 1. That's my model. So I have ACGT in some position in my genome. Radu has ACGT in his genome at that same position. And here we might hypothesize that this is independent, right? Let's pretend that this is independent. His ACGT is independent of my ACGT. So this is given by a model inside the 15-dimensional simplex on joint distributions on our nucleotides, okay? Now then there's some Lipschitz polytope and there's some combinatorial complexity. And then from the previous formula, the algebraic degrees will be 20, 60, 84, and so on. So if I knew ahead of time, for example, that that the optimal face in my Wasserstein optimization problem has dimension 3, then I need to solve a system of polynomial equations with 68 complex solutions. And doing so, I am guaranteed with proof to solve my optimization problem. Okay, so this is sort of a table that illustrates the cartoon in independence of two discrete random variables. Now we did lots of experiments. So this paper had an experimental flavor. Our co-author, Guido, is a machine learning guy, was very interested in doing some experiments for models he was interested in. So here we had various situations of 3 cube, these are models on 2 and 3 random variables with 2, 3, 4 states. We have various base distances on the graph. So there's L0, L1, I forgot what DI is. Then the corresponding polytope has an F vector. You can see here it's tiny, 3-dimensional, but some of them are quite large. The polytopes are higher dimensional. So this column F vector of the unit ball sort of indicates the combinatorial complexity. And then here we have an empirical distribution of the number, percentage of times the optimal solution occurs at a dimension, a certain face of a certain dimension, right? So we randomly picked data distributions, say uniformly in the appropriate simplex. We solved to optimality, and this is the percentage. So in each row, for example, on this polytope here of dimension 0, 1, 2, 3, 4. So we're optimizing with enlarging a 4-dimensional polytope, and 17% of the time we're landing on a facet, and 64% of the time we're landing on an edge. And here the geometry says we never land on a vertex. So this is a geometric condition. So here, for example, we never land on a face of low dimension, but then also tapers off in high dimension. Okay. Now I tried to be quick in ending in time, and maybe I was actually too quick. But the truth is, nobody minds if a math talk ends too early, right? I've never heard somebody complain about the talk ending a little early, so there's enough time for a discussion and questions. So let me wrap this up with a conclusion that in this talk, we had a statistical problem, right? We wanted to find the optimal point from the data to a model, which is independence. This is an optimization problem. It's an interesting optimization problem because it involves discrete and continuous elements. Discrete because the unit ball is a nice polytope. Algebraic geometry comes in because at the end of the day, whether you like it or not, you are solving algebraic equations, even if you don't know it, right? If you solve a global optimization problem and you sign in blood that you find the global optimum, then you have solved an algebraic system, and you've addressed the algebraic complexity problem I indicated. And of course, there are nice opportunities here for algebraic combinatorics, both on the continuous side and understanding these kind of formulas a little bit better, and on the discrete side and moving further in understanding the polytopes, the unit balls. So with that, I thank for your attention.
Thank you very much for a nice talk and clear talk, showing nice links between algebraic geometry, optimization, statistics. So it is time for questions. Are there questions? please just unmute your microphone or raise hand. So then let me ask the first question. So going back to the model, so the set capital M, so you said the set M is represented as a solution set of an equation generated by so driven by a polynomial. So polynomial equals 0. So what would change? What would happen with the sorry for that with the model in case we would have also let's say inequalities, or not just
yeah. So that's true. So in principle, we can also, of course, throw in inequalities. That makes the algebra a little more complicated, but in principle, the methods, will apply to semi-algebraic sets. So that's defined by equations and inequalities. I always try to sort of define or identify a model organism. And I think in these kind of independence models, it's equations. You can see here, this is the 2x2 determinant, right? This is a picture of a 2x2 determinant. So here's a parametric representation of this model given by two parameters, P and Q, the marginal distribution of the probabilities. But you can see this times this equals that times that. So this is really the 2x2 determinant. And then here we have the analogous equations for tensors, right? So tensors of rank 1 also have similar equations, and tensors of higher rank given by more complicated equations. So to first approximation, we kind of relax the inequalities and we work just with the equations. But of course, you're absolutely right. In many applications, we're not maybe interested in tensors or matrices of a given rank. Maybe we're interested in non-negative rank or something like this, and there'll be different additional inequalities. But this was just the first approximation as to deal with situations like this and to think about zero sets of polynomials.
So I'm also asking because semi-algebraic functions, semi-algebraic sets played an important role in optimization in the last decade. There was a development related to a generalization of the Loyasevich property. So this was a so-called Kurdika-Loyasevich property, which it played a role in improving global convergence of algorithms for non-convex problems. So we have a question by Jerome Bolt. So Jerome is asking if the manifold M has to be real algebraic.
Well, in the way we set this up here, the answer is yes, right? Because if it's not algebraic, let's say we take a trigonometric function like the sine function, then there will be the set of global solutions could be discrete but infinite, right? So the set of maximizers of a trigonometric function is typically infinite. So then we don't have tools available. We do not have this notion of algebraic degree. So to really have this notion of algebraic degree, and this being a finite positive integer, we need some algebraicity or semi-algebraic behavior. Once we're in the trigonometric setting, we would not have that.
Thank you. Are there other questions?
May I put a question, Bernd?
Sure.
It may be a silly question, but you are working with lower dimensions. How big dimension can you go? Your dimension R can be very large. Can you even approach infinite in some sense, or just?
Well, let me answer it like this. Of course, with exact solutions, we cannot go very far, right? I mean, this traditionally, there's symbolic algorithms. They're very limited. Now we can go a little bit further. But of course, we are limited by the truth, right? I mean, if we really want to guarantee to have the optimal vertex of our polytope, well, there's a very large number of vertices, right? If we want to solve the algebraic problem to optimality, these numbers become very big. Very soon they'll be in the millions and the billions. So this is what limits us. So it's the size of the true output that would limit us. But the good news is that this theory can predict this. So if you come to me with your problem, I can tell you ahead of time by evaluating these kind of combinatorial formulas how bad it will get. If it's small, then we can hope to solve it exactly. Well, if it's big, we have to do something else, right? We have to speak to the 80 experts in the audience who deal with the large-scale global optimization problems, right? Then we have to use methods that scale and maybe take locally advantage of geometric insights.
Thank you.
Thank you. Are there other questions? So you are just looking at let's say exact algorithms when solving these problems. So does it make sense to, let's say, to make use of some approximate algorithms? Or?
Absolutely. I think the problem makes sense. In fact, people are very interested in this problem. And so there's quite a literature in machine learning, and people use all kinds of methods. So this problem is interesting in its own right for any kind of model M. And the reason is that people are very interested in optimal transport as a method in machine learning. So in traditionally, people use the Euclidean distance here for these kind of problems. Then Kolberg-Leibler type distances are very important, but nowadays people are very interested in polyhedral norms, such as the Wasserstein distance. So this optimization problem is very interesting, independent of the method. What we did in our work is to examine this problem from an algebraic combinatorial perspective.
Thank you. So I got a question in the chat, but of course I'm not able to answer it. So the question is, can you explain Serge-Veronese varieties? I mean,
oh, okay. So this is simply, yes. So Segre-Veronese variety is simply, so Segre and Veronese are dead white Italians, right? So as to make a joke, but this is really simply matrices or tensors of rank 1. So the set, this is an example of a Segre variety. So the set of all matrices or tensors, or these are in the literature called Segre-Veronese varieties. So in general, maybe I have a 5 by 3 by 3 by 4 tensor, but the two middle threes I have symmetry, right? And so there's a mix. So Segre refers to general tensors, Veronese refers to symmetric tensors, and then if I mix them up, we call them Segre-Veronese varieties. So this is simply Italian geometers jargon for a rank 1 situation.
We have another question by Jerome. So Jerome, do you like to ask the question? Should I read it? Okay. Okay, so then I have to read the question. So can we hope that the sparsity assumption on the polynomial defining the objects as M would make the degree small even in high dimension?
That is a very, very good question. And I think the answer is yes. Well, first of all, we can always hope, right? In every human situation, we can hope. Now, the equations here that define the model are already very sparse, right? Because these are really 2 by 2 determinants, right? So here, the equation, so this picture, this is the 2 by 2 determinant. Even for a very large tensor, we have a very, very sparse equations, but there could be additional geometric sparsity structure. So the additional structure that we could have significant sparsity in the underlying metric, or we could have significant combinatorial structure in the data, and that will drop down the complexity. And so this was hidden here in my slide in this phrase, both in relative general position, okay? In practice, especially in computer science practice, things are never in general position. Things are in very special position. So there's versions, one can try to extend this theorem to situation where the data is not general, and then these numbers will drop down. And then these degrees will drop a lot, and then one can hope to go further. So here, so again, the equations of the model, because the independence model are already super sparse, but there's additional structure to be gained from what we know about the underlying metric, finite metric, and what we know about the data.
So may I ask, so in each way, one would have to define sparsity in order to really simplify the model. So is this necessary to be very precise, or like there are many ways to define sparsity?
Yeah, I mean, for me, sparsity means a highly structured, polynomial or matrix. So traditionally, a matrix is sparse if it has lots of zeros, or a polynomial is sparse if it has few terms. So that's one notion of sparsity. Of course, there's other notions of sparsity we could have. So I would say, in principle, this is compatible with any notion that you come up with. The only point I was trying to make, that since here we focus on independence models, rank 1 in independence is already a pretty sparse situation in these traditional senses.
Sure. Okay, thank you. Are there other questions? Then I propose to stop here. I would like to thank very much the speaker again for a very nice talk, a very nice and interesting topic. We will post the slide and the video on our website. So I just want to announce that our speaker next week will be Janier from University of Victoria, Canada. So I want to wish you a nice week. And yeah, our hope is to be able in near future to invite all the OWOS speakers to Vienna for a meeting here in Austria, and hopefully this will be possible very soon. So thank you very much for a nice talk. Thank you for accepting our invitation.
Thank you very much. Bye bye and stay healthy.
Bye bye. Thank you.